So let's continue our discussion in Geotechnical Engineering with the topic stresses in soil. So let's focus on the stress in saturated soil with seepage. And there are two scenarios here. We have the first one, the upward seepage, and the second one is the downward seepage. So it should be downward. Okay. So downward seepage. So let's see how these calculations here were get using this system. So looking at this system, this is an upward seepage because of the inflow of water from the bottom of the soil setup. Okay, so let's first solve for the hydraulic gradient of the entire system. Now, if we say hydraulic gradient of the entire system, it means that we are considering the whole length of soil or the whole height of the soil H2. Now, if we are considering H2, we are focusing on this tube inserted at the very bottom of the soil setup. And we are to get the head from this water level. So from this water level of this tube attached from the bottom and the water level at this portion. So we get here the value of H. So hydraulic gradient I. The hydraulic gradient I of the entire system is equal to H divided by the total height of the soil, H2. Next, we get the point A. Let's find the P total at point A. So at point A here is this one here, and take note that this portion H1 is water and H2 is soil. So at point A, P total is equal to the gamma of water multiplied with the height of the water. So that's the only pressure that is being encountered at point A. Now we get the pore water pressure. We have there gamma W H1. Thus, if you get the P effective, that is P total minus PW, P effective is 0. Next, let's go to at point B. Okay, so at point B, here, this location, if we are going to get the calculations for the P total, PW, and P effective of point B, we need to insert a tube here at the level of point B. Now this tube, inserted tube here, has water level up to this point, and that water level and the water level of the outflow has a head of H sub 1, small h sub 1. Okay? So if we get the P total at point B, that is equal to the gamma of water, the H1, the height of the water, plus the gamma sat of the soil, times up to the point where we reach the point B, and that is Z sub 1. Next, we get the PW. So for the pore water pressure, okay, so let's create some space. Right, so for the PW, for point B, we have there gamma of water, of course. And let's take the total height of the water from the level of water from this tube down to the point B. So that is equal to H1 plus H sub 1, the bigger H, then plus Z1. So that's the total H for the point B, for the water of point B. Okay? So we have there H1, small h sub 1, plus the big H sub 1, plus Z sub 1. So that's for the PW of point B. Next is the P effective. So P effective is equal to P total minus the PW. Or in shortcut, we have there the gamma B of Z1, okay, minus gamma water H1. So we can have this as a shortcut formula in computing for P effective. So we get the gamma effective. Gamma effective is gamma sat minus the gamma of water. Next, we have the point C. So at point C, you see the location of point C is at the bottom of the soil setup. So the tube attached to it, or the one we are in concentration of, is this tube at the bottom. Okay, so let's compute for point C. The P total for point C is, so from the top, you have there the gamma of water, big H sub 1, plus the gamma saturated of the soil, and the total height of the soil H sub 2. P water is equal to the level here up to this point C. So this is the H that we are computing for pore water pressure of point C. So we have there gamma water times H plus H, big H sub 1 plus H2. So that's the pore water pressure for point C. Now P effective is equal to, again, that is P total minus the PW, or if we wanted the shortcut, we get the gamma effective of the total soil height minus the water. So gamma of water multiplied with the head from the tube. Okay. So that's the shortcut formula. So that's for the upward seepage. Okay, so that is the upward seepage. So that's how we arrive at this formula. Now at this portion here, it's just simply a ratio and proportion. So why ratio and proportion? It was taken from here. So if we are considering the entire system, I, for the entire system, we have there H over H sub 2, right? For this tube here, located at the bottom. If we take the tube at the point B, we can have that as H sub 1 over Z sub 1. So we have there, if we want to have the value of H sub 1, that is equal to, so H sub 1, that is equal to, we have there I Z1, or that is equal to, you have there H, so Z1 H over H2. Okay, so that's how we get this one here. Remember that I is, it should be Z sub 1. Okay. Alright. So, you get the idea. Let's go to the downward seepage. For the downward seepage, so this is how the formulas in this study guide was taken. So let's solve for this one here. For the entire system again, so we have there the hydraulic gradient I. And we are to focus on the tube inserted at the bottom of the soil setup. Okay. And we have there the downward seepage because water is flowing out at the bottom of the setup. This is the inflow and then this is the outflow. Alright, so what happens here is the tube inserted at the bottom will have a downward H, small h here. And then we have here the height of the soil, the total height of the soil, H sub 2. So we have now our hydraulic gradient for the entire system as H, small h, the difference of the water level from the tube and to the inflow. So we have there H over H sub 2. Okay. Next we have at point A. Solve for the P total at point A. We have there gamma of water times the height of the water. For water, we have gamma water and then H1. So P effective now is equal to P total minus PW equals 0. At point B, so at point B here, again, we have P total equal to gamma of water, H sub 1 plus the gamma sat of the soil, and then Z1, the location from the top of the soil up to the point B. Then PW, so PW is equal to D, so this is concentrated in this tube here. So just as we did a while ago, we got the value of H for B here. So this is the H. So we added H1, H1, then H2 to get the value of H. Now for the downward seepage, where is the level of the water from the tube that is inserted on point B? So this portion here. So this is the H that we need to calculate. Now how do you get the value of H there? So gamma water times. So what we do here is we get H1 plus Z1 minus H1 in order to get the value for H. Okay? So that's how we get the formula. Next, we have the P effective is equal to P total minus P water. So P total minus P water, or we can have the formula, the shortcut formula, gamma effective Z1, then we have here plus gamma of water H1. Okay? So previously on the downward seepage, we have here minus. But in the downward seepage, we have the plus. So see the difference. So at point C located at the bottom of the setup, so we get the P total equals gamma of water, height of water, plus gamma sat of the soil, total height of the soil. P water is equal to Again, let's concentrate on this tube here, inserted at the bottom. The H that we need for point C is this one here. From the water level of this tube up to the point C. So how do we get that H? So we have here gamma of water times. So we have there H1 plus H2 minus the small h. So that's how you get the value of H. Okay. Next, we have the P effective. P effective is P total minus P W, or we can have the shortcut formula of gamma effective total height of the soil plus gamma of water and the small h there. Now again, difference, this downward here has a positive sign, the upward has a negative sign, minus, and we have here plus. Okay, so that's how we arrive to that formula found in our study guide. Let's go to the effect of capillary rise to soil stress. So there is an effect to the soil stress when it comes to the capillarity. So capillary rise in soil is demonstrated on the following figure. A sandy soil, so this soil here, is placed in contact with water. So water is located in this container. After a certain period, water rises and the variation of the degree of saturation with the height of the soil column caused by capillary rise is approximately given in the figure. So the soil inserted in this water experiences a capillary height of H2. So how do we get the value of H2? So another information here, the degree of saturation is about 100% up to height H1. So up to height H1 here. Beyond the height H1, water can occupy only the smaller voids. Hence, the degree of saturation is less than 100%. The approximate height of capillary rise is given by Hazen as H sub 2 equals C over E D sub 10, where D sub 10 is the effective grain size, E is the void ratio, and C is a constant that varies from 10 to 50 square millimeters. The pore water pressure, or PW, at a point in the layer of fully saturated by capillary rise is PW equals negative gamma of water times height. So the difference from the previous computation that we are doing is that it has a negative sign for the capillary zone. Remember that when we are solving for P water, the P water positive is located wherein the soil is submerged in the water. Now when it comes to the region of the capillary rise, we have a negative PW. Okay? If a partial saturation is caused by capillary action, the pore water pressure PW can be approximated as negative degree of saturation times gamma of water times the height of the capillary zone, where S is the degree of saturation at the point under consideration. Right? So consider the soil layer shown. So let's consider this soil layer. So in our study guide, there's already a calculation there. So let's see how these calculations were derived or computed. Okay, so we have here the soil layer. So if we are to solve for point A, so at point A, so point A is located here, it's located H1, H sub 1 plus H sub 2 from the soil surface. So this is the ground surface here. And then this is the water table. So this water table here, we get the capillary rise from this water table at a certain height H. So capillary rise, or this is the capillary zone H. Okay? So as you can observe, point A is located inside the capillary rise. So how do we get the computation for point A? So at point A, we get the P total equals the gamma 1 here times the height H sub 1. Plus, we have there at this portion the gamma 2. Then we have H2. That's the P total. Let's go to the PW. So this portion here will differentiate from the previous calculations that we had. The pore water pressure, if you recall, pore water pressure is present if the point is located that is submerged in the water. But this time, point A is located at a capillary rise, the capillary zone. So how do we treat this? It says there in the study guide, that is, PW is negative gamma WH. But if there is a partial saturation, we will use this formula. So let's say that it has a degree of saturation S sub 1. So PW now here is negative S sub 1 gamma of water, and the location for H here is H3. H3 is found from the water table up to the point A. Okay? So it's not H2, it's H3 located from the source of water. So that's for the PW. Next, at point B. Now at point B, so the P total for point B, so point B is located at the surface of the water table. So we have there gamma 1, H1 plus gamma 2 and then H. Okay? Then we have P water, pore water pressure is equal to 0 at the point of the water surface. So cannot compute for the pore water pressure there. At point C, P total is equal to gamma 1 H1 plus gamma 2 H. So gamma 1 H1, then gamma 2 H. Then for this part here is gamma 3 H4. So plus gamma 3 H4, and then P water is equal to positive gamma of water. It's already submerged, so there's no need to put S there because S is automatically equal to 1 if fully saturated. So that's why we have there gamma W H4. So that's how we get the formulas or the calculations here in this study guide. Now let's go to the examples for the continuation of the solving of the examples. Now we are in number 6. So we already solved examples number 1 to 5 in the previous video. So let's continue here in number 6. A dense silt layer has the following properties. Void ratio is equal to 0.40. Effective diameter, or D sub 10, is equal to 10 micrometer. Capillary constant C is equal to 0.20 square centimeters or centimeter. And we have here the free groundwater level is 8 meters below the ground surface. Now visualize the given scenario. We have here one soil type, and it is a silt. So we have here silt layer. If we draw that. Okay, so let's just put here something like this. So that's the silt layer. Silt. And then it says there, free groundwater level is 8 meters below the ground surface. So let's change this into a color blue. Say this is the groundwater surface. Okay. Symbol for the water. So, or let's just say this is the water table. And it's located 8 meters below the ground surface. So this is 8 meters below the ground surface. Alright? And we have there void ratio is equal to 0.40. The capillary constant, effective diameter. Find the height, for letter A, find the height of capillary rise in the silt. Capillary rise is given as H is equal to C over E times D sub 10. Letter B, find the vertical effective stress in kilopascal at 5 meters depth. Assume unit weight of solids equals 26.5 kilonewton per cubic meter, and that the soil above the capillary action rise and ground surface is partially saturated at 50%. Find the vertical effective stress in kilopascal at 10 meters depth. Assume unit weight of solids 26.5. Okay, similar condition with the letter B. Okay, first let's compute for the capillary rise of the soil, and the formula is already given. So for letter A, capillary rise, H is equal to C over E D 10. Given the value of C as 0.2 or 0.20 square centimeters. So 0.20 square centimeters. So we need to convert first micrometer D sub 10. Okay. Convert first D sub 10 because D sub 10 is 10 micrometer, and that is equal to 10 times 10 raised to negative 6 meters. So we multiply this with 100 centimeter divided by 1 meter. Okay, so we have there D sub 10 is equal to 10 times 10 raised to negative 4 centimeter. Okay, centimeter. So we have here C as 20 square centimeters. E is 0. Or void ratio is 0.40. 0.4, and then D sub 10 is 10 times 10 raised to negative 4 centimeter. So we have here 20 over 0.4 times 10 times 10 is 94. Oops. Okay, so that is equal to oops, 10 micrometer void ratio. Okay, so that is this is there 50,000. So 0.2. Sorry, my calculator is, so it should be 0.20. I put there 20. Okay, so 0.20 square centimeters. So I was wondering why it's showing a very large number. So 500 centimeter, or that is 5 meters for each. Okay, so we have here the value for the H, or the capillary rise, is equal to 5 meters. Let's draw here a broken line. This is 8. So this is a capillary rise. I'll just put it here just to indicate. Right, so that means we have here this is 3 meters, and then this is 5 meters for the capillary rise. So that's for letter A. Now let's go to letter B. We need to compute for the vertical effective stress in kilopascal at 5 meters depth. So 5 meters depth from here. So we will be deleting some. So at 5 meters depth, okay. So 5 meters here, and let's put that point A. Point A. Assume unit weight of solids. Pay attention, since their unit weight of solids did not mention if it is gamma M, gamma sat, gamma dry. It just says their weight of solids, unit weight of solids is 26.5 kilonewton per cubic meter, and that the soil above the capillary action rise on the ground surface is partially saturated at 50%. So S here is 50%. Right? So let's solve for the vertical effective stress. So we need to find the P total minus the P water here. But first, let's find what is the gamma. What gamma are we going to use when we are considering the zone of the capillary action, the capillary rise here. So let's find for the gamma sat. Okay. Gamma sat for the So we need to find the gamma M here because we have a partially saturated soil, and we need to find the gamma sat here first. So gamma M, how do we compute for gamma M? It says there, so we need for the formula for gamma, we have G plus SE over 1 plus E. So void ratio is already given. What is missing from the formula is the specific gravity. So gamma M is equal to G plus SE over 1 plus E gamma of water. So we are missing a specific gravity, and we can solve that with the given unit weight of the solids. So you recall from the basic formula, specific gravity is equal to the unit weight of the solids over the unit weight of water. So we have there equal to 26.5 kilonewton per cubic meter over gamma of water is 9.81 kilonewton per cubic meter, and that is equal to, so G now is equal to 26.5 divided 9.81, it is 2.701. So we can now solve for gamma M. Okay, so let's erase here. So gamma M now is equal to G plus SE over 1 plus E gamma of water. That is equal to 2.701 plus partially saturated 0.5. The void ratio is 0.4 over 1 plus void ratio 0.4, gamma of water 9.81. So what is now gamma M? Gamma moist. So gamma moist is equal to 20.33 kilonewton per cubic meter. Next, we solve for the gamma sat. For the gamma sat, we have G plus E over 1 plus E gamma of water. The reason why we have here E is because S is equal to 1 for saturated soil. So that is equal to 2.701. So in your calculator, you just have to remove 0.5, then leave there 0.4. 1.4, 9.81. So gamma sat is now equal to 21.73 kilonewton per cubic meter. Now finally, we have our gamma moist and gamma sat. So what's next is we compute for the P total. So the P total for point A. So P total now is equal to, okay, let's go back. Gamma M times 5 and then gamma sat times, no, it's not times 5. So we need, so if this is 3 and then this is 2. So this is 2 meters here. So let's extend this one. Okay, so this now is 2 meters and this is 3 meters. Alright? So gamma P total for point A is gamma M times 3 times plus gamma sat times 2. Okay, so gamma moist is equal to 20.33 times 3 plus 21.73 times 2. So P total at A, P total at A is equal to 104.45. The unit is kilopascal. P water at A. So let's go back again. What's P water at A? Is it 0 because water is located at this portion here? No, it's not 0. Rather, we will get the PW here from the water table surface up to the point A. So our H here, the H that we are going to use is 3 meters. Okay. So 3 meters. So PWA is equal to, and how about the S? Because we found out a while ago that it is negative S gamma WH. What about S? In the problem, it says there that the ground surface and the above the capillary action rise is given as 50%. We therefore conclude that the S for this portion is equal to 100%, because it did not mention if it's partially saturated or not, but rather it says there only the above. So S is equal to 100%. So S is equal to 1. So negative 9.81 times the H, how much is the H there? 3. So P water at A P water at point A is equal to negative 29.43 kilopascal. Therefore, we have P effective at A is equal to 104.45 minus 29, or should I say minus negative 29.43. So it will result in addition, and the answer here is 133.88 kilopascal. So that's the P effective for point A. Now let's go to the letter C. Find the vertical effective stress in kilopascal at 10 meters depth. And then same condition as point B. 10 meters depth. So this is the ground surface. Then 10 meters depth. So another extra 2 meters. Okay. So this is 10 meters. Let's name this as point B. Okay. So at point B, you see that it's already submerged. It's located below the water table. So this is our water table here. So let's compute for the P total. P total, or we can just simply create a shortcut of this. If you go back to our calculations in the first video, we were able to obtain how to compute without going through the P total and PW. So we will just take here the gamma M plus gamma M times the height 3 meters, because that is moisture. But pay attention at the capillary zone. At the capillary zone, we get the gamma sat times 5. Then, when it comes to this portion here, because this is 2 meters below the water table, we get a gamma sat. Obviously, we get a gamma sat here, and we will deduct gamma of water. Okay? So again, let's remind ourselves. If we are taking gamma m, we put it as itself. For gamma sat, when it's located in the capillary rise, put it as is. Okay? But as for the gamma sat submerged, we reduce the gamma of water. Okay? So it's something to remember. Let's go here. Letter C. P effective at B. Now gamma M is 20.33 times 3. Next, in the capillary zone, we have there the gamma sat 21.73 multiplied with the height of the capillary zone. So this is gamma M, gamma sat. Now, take note when we are considering the gamma sat that is submerged in the or that is below the water table, 21.73 minus 9.81 times H, that is 2 from the water table. So this is gamma sat and this is gamma of water. So P effective at point B is equal to 193.48 kilopascal. Okay, so that's for number 6. Okay, so get a screenshot. So that's for number 6. Let's go to number 7. A borehole at a site reveals the soil profiles shown below. So they dug, they inserted the tube, and then they were able to obtain the soil profile up to 20.6 meters, or is this meters? So it is 20.6 meter depth of hole. Okay, and with this soil profile, so we have there the different kinds of soils. We obtain here, the layer 1 is very fine wet sand with silt. Layer 2 and 3 are the same soil type. So layer 1 is different. Layer 2 and 3 is the same. And then layer 4 is another different kind of soil, soft blue clay. So fine sand for layer 2 and 3. The only difference between these two layers is that layer 3 is the, or layer 2, I should say layer 2 is saturated by capillary action. So the symbol here signifies that water table is located 3 meters depth from the ground surface. Okay, so this is the same soil type. The difference is layer 2 is a capillary zone. Then given G, or specific gravity, 2.7 for all soil types. Letter A, what is the unit weight of the soil in layer 1? So if we're talking about unit weight of the soil layer 1, so this is a different type of soil with given moisture content of 5% and a degree of saturation of 40%. What can you conclude now? What can we conclude for the unit weight of layer 1? Unit weight of layer 1 is gamma moist. So we're going to solve for gamma moist. B, what is the effective stress at a depth of 2 meters below the ground surface in kilopascal? 2 meters below the ground surface, it's located here in between soil or layer 1 and layer 2. Let's name that as point A. Okay, so let's name that as point A. Next, letter C. What is the effective stress? So, let's put here what is the effective stress. PA sub A. So, C. What is the effective stress at a depth of 20.6 meters below the ground surface? So, that is from this ground surface here downward. So, we're looking for the P effective of this point here. Let's name that as point B. Point B. Okay? So, P effective B. Okay, so let's solve for soil 1 first. For soil 1, layer 1, gamma M. So, gamma M is equal to G plus, since given here is moisture content, so GMC over 1 plus E gamma of water. Now, the problem here is, what's the value of E? But given S. So, we can solve it by the formula GMC equals SE. G is 2.7. Moisture content is 0.05 because it's 5%. Equals the degree of saturation 40%, so 0.4. Then E. E now is equal to 0.3375. So, from the formula, gamma M is equal to 2.7 plus 2.7 times 0, MC. MC is 0.05 all over 1 plus 0.3375 times 9.81. So, gamma M, gamma moist is equal to 20.79 kilonewton per cubic meter. So, that's for letter A. Letter B, what is the effective stress at a depth of 2 meters below the okay, so what do we need to find here is the value of gamma sat. Gamma sat for the layer 2. So, gamma sat question mark. Because gamma moist is located there at layer 1 because of the presence of S is equal to 40%. So, what is gamma sat for layer 2? So, let's solve for the gamma sat first. Letter B. So, gamma sat is equal to G plus E over 1 plus E. Gamma W, gamma sat 2.7 plus 0.3375. No. We cannot use 0.3375. The reason here is it is a different soil type. So, if it is a different soil type, therefore, let's resolve for E. So, GMC S E. So, moisture content so the moisture content is given as 0. This one here, that is 12%. So we have there. So since this is different, this is the same soil type. Therefore, the condition here given is the same with layer 2. So we have there 2.7, MC is 0.12 equals the degree of saturation there is 1 and E So we find the value of E as 0.324. Okay, so that is for layer 1. I think, yeah, what's the question here again? Okay, so let's get the value first. Gamma sat equals 2.7 plus 0.324 all over 1 plus 0.324 times 9.81. Gamma sat here is now equal to 22.405 kilonewton per cubic meter. So this gamma moist here is for layer 1. For this gamma sat here is for layer 2 and 3. 2 and 3. Okay. Okay, I think we got it now. What's the question again? Effective stress at point A. So effective stress at point A, P total of point A is equal to, we have the gamma moist, 20.79, so that is 2. That is equal to 41.58 kilopascal. Then it's P total A. P water A is equal to, so we cannot do the shortcut. We're not doing the shortcut when there is a capillary zone involved. Now, since point A is located 1 meter from the water table, so 1 meter from the water table, so PW is negative S, or let's just put it as 1. So gamma water H, so negative 9.81 times H1. So P water at point A is negative 9.81 kilopascal. Therefore, P effective now at point A is equal to P total 41.58 minus negative 9.81. So P effective at point A now is equal to 51. So 51.39 kilopascal. So P effective at point A. PEA. Now letter C. Letter C question is, what is the effective stress at point B? Okay, point B. So this is the one we can do the shortcut because the point is not located at any capillary zone. Okay, so we can do the shortcut now. What we will do as a shortcut here, let's get gamma M. Gamma M multiplied with 2 meters. Next, we get so we have the gamma M, the gamma sat. The gamma sat located here at the capillary zone. But we will not reduce water. So gamma sat as is at the capillary zone. Next, we have here the submerged in the water already. So gamma sat minus gamma of water. And then another soil type, gamma sat minus gamma of water. Now speaking of another soil type, let's find also the gamma sat. The gamma sat of soft blue clay. So what is the gamma sat of soft blue clay? Given a different MC or water content, moisture content at 28%. So let's solve for gamma sat for the layer layer 4. So gamma sat of layer 4 cannot solve gamma sat first because we need the value of E. So GMC SE. G is 2.7 for all soil types. We found there 28 at MC. Submerge, so S is equal to 1. Have their E. So moisture or void ratio is now equal to 0.756. Gamma sat is now equal to G plus E all over 1 plus E times water. So gamma sat is now equal to 19.307 kilonewton per cubic meter. Okay, so finally we have now the gamma sat of layer 4. So let's solve now for P effective B. Gamma moist a while ago is 20.79 times 2 plus the gamma sat at the capillary zone. So that is 22.405 times 1. And then the gamma sat, same soil type, but this time submerged in water. We have there 22.405 minus gamma of water, 9.81 times, what's the height here? The height here is 5.4 minus 3. Okay, so 5.4 minus 3. 5.4 minus 3 plus the layer 4. Layer 4, the gamma sat minus gamma of water, 20.6 minus 5.4 for the height of this one. Okay? So gamma sat here is 19.307 minus 9.81 times 20.6 minus 5.4. So P effective at point B is equal to 238.567 kilopascal. So P effective at point B. So that's for letter C. Okay, so that's number 7. Screenshot first before we proceed to the next question. The next, number 8. Now how many items we have here? 9, 10, 11. So there's 11, up to 11. Number 8. Consider the upward flow of water through a layer of sand in a tank shown below. For the sand, the following properties are given. The void ratio E is equal to 0.4, G, specific gravity G, 2.67. Calculate the effective stress at point A, so PEA, this one here. Next B, calculate the effective stress at point B, so P effective B, so located at the bottom of the tank. Then C, calculate the upward seepage force per unit volume of soil. So we have a formula for that. Right, so let's compute first for the soil. What's missing here? We are taking the effective stress. We need the gamma sat. There is no gamma sat given, so let's solve for gamma sat first. So gamma sat is equal to, so G plus E, 1 plus E, gamma W, G is 2.67 plus 0.4 over 1 plus 0.4 times 9.81. Gamma sat is now equal to 21.51 kilonewton per cubic meter. Okay, so we got the first one. Alright, so effective stress at point A. Remember in our study guide, here we go, upward force. So remember this tube here. To get the value of for the point B here, we need H sub 1. So we need the H sub 1 for the pore water pressure. Right? So this is point A. Let's have the tube inserted here. Okay, let's have there. Oops. Okay, so there you go. We have their tube inserted here at point A, and then the water level, let's assume that the water level is in here. So we need to find the value of, let's name this as the H. Yeah, that's H, small h. Let's name that as small h. So we need to find here the value of H sub A. How do we compute for that? So if we name this as H sub A, this layer here, let's name this as the total height of this water column here. Let's name that as H sub A. HA. So I hope it is clear. Let's put here H, and then this is H sub A. Alright? So how do we get the value of that? We can use the entire system. So using the entire system. So if 1.5 is located from this point here up to the water level there, H is located at this point of the water up to the water level here at the overflow. So we can have a ratio and proportion using the entire system. For letter A, I, for the entire system, we have there I is the head of the total soil, 1.5, taken from the tube inserted at the bottom of the container or the tank. So 1.5 divided by the total length of soil is 2 meters. So 1.5 over 2, that is also equal to the smaller the point A, the tube inserted at point A we have there H over, so H over, we have there what's the distance? 1 meter. So H now is equal to 0.75. Okay, so we now have the value for that. So that is 0.75. Okay. So we got there. Let's do the shortcut. P effective is equal to, P effective at A is now equal to the gamma buoyant. So gamma buoyant of the soil. So I think it's much better if we show the long method first before the shortcut. So P total is equal to the gamma of water, 9.81 times 0.7 plus the gamma sat of 21.51 times 1. So what is the P total? That is 28.377 kilopascal. Let's get the value for P water. P water is equal to 9.81 times the total HA. So we have there 0.75 plus 0.7 plus 1. Okay. So that is equal to 0.81 times 0.75 plus 0.7 plus 1. So 24.0345 kilopascal. So P effective now is equal to P total minus P water, or pore water pressure, is equal to 28.377 minus the answer. So 4.343 kilopascal. So P effective A. Okay. Or we have the solution P effective A, the shortcut, the gamma buoyant or gamma effective here. The soil first, the soil. So 21.51, the gamma buoyant, minus 9.81, multiplied with the height of that soil, 1, minus water, 9.81, and then the H of the water, that is 0.75, that is here, the head. So P effective is now equal to 21.51 minus 9.81 minus 9.81 times 0.75. The answer is same, 4.343 kilopascal. So you can use this or the shorter one. So that's for letter A. Let's go to letter B. What is being asked in letter B? Calculate the effective stress at point B. So let's concentrate point B. So at point B, we have the P total A, point A. So P total at point B is gamma of water 9.81 times 0.7 plus the total height of the water, the soil, sorry. So the gamma sat 21.51, the total height of the soil is 2. So P total is equal to 49.887 kilopascal. Now we have pore water pressure at point B, that is equal to 9.81 times, so pore water pressure is 1.5 plus 0.7 plus 2 until it reaches the bottom. So 1.5 plus 0.7 plus 2. That is 41.202 kilopascal. So P effective B, point B, is equal to P total minus pore water, that is equal to 8.685 kilopascal. Okay, now letter C. For letter C, we have there calculate the upward seepage force per unit volume of soil. So the seepage force, should be, so the seepage force per unit volume of soil is equal to I, or the hydraulic gradient, times gamma water. So the hydraulic gradient is, a while ago did we compute the hydraulic gradient? So this is equal to 0.75. So I is equal to 0.75 times gamma of water 9.81 is equal to 0.75 times 9.81, 7.3575. The unit is kilonewton per cubic meter. Okay, so that's for number 8. Let's go to number 9. Consider the downward flow of water through a soil layer or through a layer of sand in a tank shown below. For the sand, the following properties are given. E is equal to 0.48, G is equal to 2.7. Determine the saturated unit weight of sand in kilonewton per cubic meter, so gamma sat. Calculate the effective stress at point A, so PEA. Calculate the effective stress at point B, so PEB. So point A, then point B. Right? So we need to do the same thing a while ago. Letter A. We need the gamma sat. So gamma sat is equal to G plus E over 1 plus E. So 2.7 plus 0.48 all over 1 plus 0.48 times 9.81. Gamma sat is 21.078 kilonewton per cubic meter. Okay. Letter A is solved. B. Determine the effective stress at point A in kilopascal. So it's looking for point A here. Again, we need to insert a tube. Okay, so where can we draw that tube? Let's draw the tube here. Oops. Okay, so we have there the tube inserted at point A. And since it's an outflow, downward seepage, we can have the location of the water level of water that is below this level here. So we can name that as, for a better drawing, we inserted here a tube. There you go. And then this is the water level we want to project. So this is color. So let's name this H, this downward part here. So this is H. Then let's name here HA. This level of water up to this point here at point A, let's name that as H sub A. Okay. I hope that is clear. Alright. Because we need to find first what is the value of that H. Right, for I, or hydraulic gradient, for the entire system, we need to consider this tube here that is inserted at the bottom of the tank. So 1.2 meter for the head, and then the total height of the soil is 2.5, and that is equal to the tube inserted at A. We have there H, and the total height of the soil up to the point A is 0.8, is equal to, so what is 1.2 divided by 2.5? 0.48 for the I is 0.48. Now for the H is equal to 0.48 times 0.8. 0.384. So that is 0.384 meter. Alright? So we need that in computing for the water, because in the study guide for the downward seepage, at point B here, you observe that for the pore water pressure here, we need the value for H sub 1 there. Okay. So let's solve for the P total. P total up to the point A. So P total up to point A is now equal to water first, 9.81 times 0.6 plus 21.078 times 0.8. P total at point A is now equal to 22.748 kilopascal. Next, we have pore water pressure at A, that is 9.81. We are actually looking for the HA, value of H sub A. And the value of H sub A is, that is equal to the height here, the total height here, then minus the H. Okay, so that is your HA. The total height is equal to 0.6 plus 0.8 minus 0.384. So P water at point A is 9.81. 0.6 plus 0.8 minus 3.384. So that is 9.967. 9.967 kilopascal. So P effective A is now equal to P total minus P water, and that is equal to 22.749 minus 9.967, that is equal to 12.78 kilopascal. Or again, we can have the shortcut. P effective at point A is equal to the okay, so we have there, yeah, it's actually the same. That is 0.8. So 0.8. Then we have 21.078 minus 9.81. And then plus H1.84. Okay, so I forgot. So we have there 0.8, should say the gammas at first 21.078 minus 9.81, 0.8. Then a while ago we said that the shortcut for this is positive, whereas the upward is negative. So we will put here plus 9.81 of the water H, 0.384. So P E is the same, 12.78 kilopascal. Okay. Now let's go to letter C. P effective at point B. So P effective at point B, let's go first for P total at point B. So gamma of water 9.81 times 0.6 plus 21.078 times the total height of the soil is 2.5, and that is equal to 58.581 kilopascal. Point B. Okay. Next, pour water at point B is equal to 9.81 times pour water for point B is, we have here, we need to find H sub B. Yeah. So to get the value of H sub B, here we need to add 0.6 plus 2.5 minus 1.2. Okay, so 0.6 plus 2.5 minus 1.2, and that is equal to 9.81. 0.6 plus 2.5 minus 1.2, 18.639 kilopascal. Therefore, P effective At point B is P total minus P water is equal to 58.581 minus 18.639. So that is now equal to 39.942 kilopascal. Right, so that's for P effective point B. Okay, so we're done with number 9. Let's go to number 10. A cut is made in stiff saturated clay. So originally, so this is a clay layer. So we have here as a clay layer, and then we have here sand. Okay. So what happens here is, in this clay layer, it is cut here. Okay. So that's the scenario. So a cut is made in stiff saturated clay that is underlain. Again, the word underlain. The clay has a sand layer under it, so as shown below. Letter A, calculate the total stress at point A. So point A here is here, go. As a function of H, because where is that? H here is, the value of H is not given, so we will get the value for total stress at point A as a function of H. So P total at point A. Next, calculate the neutral stress at point A. P water. C, calculate the height H in the cut so that the stability of the saturated clay is not lost. So value of H. Okay, so let's start to solve first for letter A. We can solve for P total at A already. P total at A is, we have the value 9.81 because it is under, it has water over it, so 9.81 times each plus the saturated clay given as 19, and what is this portion here? This is 7 minus 5, so we have there 2 meters. So 19 times 2. So P total now for point A is equal to 38 plus 9.81 H. It says there as a function of H. B. Okay, so letter B, calculate the neutral stress at point A. So the neutral stress at point A is, we will consider it a saturated, there's a tube here, given tube here inserted on point A, and in this tube we see a rise in the water pressure of 4.5 meters. Therefore, it is no mystery now as to the pore water pressure, and that is 9.81 times the column of water, 4.5 meters. So that is equal to 44.145 kilopascal. Letter C, calculate the height H of water in the cut so that the stability of the saturated clay is not lost. So for the condition of stability, so this is here, for loss of stability, P effective must be equal to 0. For loss of stability, PE or P effective is equal to 0. Now we know that P effective is equal to P total minus P water. So let's equate 0. So put here 0 for PE. And then P total is 38 plus 9.81 H minus P water of 44.145. So P or H now is equal to 44.145 minus 38 divided by 9.81. So we got there 0.626 meter. H is equal to 0.626 meter. So that the soil is stable. Okay, so if H goes up higher, then the stability will be lost. Right? So that's for number 10. Now last we have the number 11. For the system shown below, so this system here, L is equal to 1.2 meters. 1.2 meter. Okay, let's put the values. So that okay, so L is equal to 1.2 meters. So let's just put here 1.2. H is 2.3 meters. H here. Okay, so that is 2.3 meters. And Y is 1.9 meter. So 1.9 meter. What is the effective stress at point A where Z is 0.7 meter? So Z is 0.7 meter. So what is the effective stress here? And then given, so notice that gamma sat is already given. So let's compute for the effective stress. P total is equal to we have the water 1.9 meter, or that is 9.81 first. 9.81 times 1.9 plus the soil is 19.5 saturated, then 0.7. So that is P total 32.289 kilopascal. Then let's go to P water. Now in order to compute for P water here, we need the value for HA. Alright, so what is the value for HA? So again, let's insert a tube here. So this is the tube. And then the location, since it is a downward seepage, so this is the water level, should be below. So this is now the level of the water. So we're looking for HA here. What's the value of H sub A? Now, to get the value of H sub A, we need to have here 1.9 plus okay, so we need the value for each one. So H, yeah, let's name this as H1. So what is H1 here? So for HA, we will need to get here 1.9 plus 0.7 minus H1. So how do we get H1 again? So H1 is by the whole system, I, hydraulic gradient, I. For the entire system, we have there the H, 2.3 over the total height of the soil, 1.2 equals H1 all over 0.7. Remember, the reference point for 2.3 is at above. So the same is true with H1. The reference point is above also. So H1 is now equal to 2.3 times 0.7 over 1.2, 1.3417. 1.3417 meter. Okay? So we now have here P water is equal to 9.81 times 1.9 plus 0.7 up to the point A here minus H1 of 1.3417. So P water now is equal to 9.81, 1.9, 0.7 is 1.3417. So 12.344. 12.344 kilopascal. Therefore, we have the P effective now as P total minus P water is equal to 32.289 minus 12.344 is equal to 19.945 kilopascal. That's the final answer. Okay? So that's number 10, and that is the last item for this video. Stay tuned for the last part of the video or the lecture series for soil stresses. Okay?